Okay, so the plan for today is to finish up 3.1 and start into 3.2. Just continuing with our discussion of numerical descriptive measures. The quote of the day today is that one physical test is worth 1,000 expert opinions. And I think this is kind of, meshes nicely with statistics or really any of kind of the hard sciences, things like chemistry or physics or any of that. You could have the most beautiful theory, you could have the most uh, highly regarded person touting that theory, but if it disagrees with actual physical evidence, that then it's just a theory that hasn't really panned out. So, the kind of the proof is in the pudding. There's a reason that we are so data oriented. Some good reasons, some bad reasons, I suppose, but there are some good reasons that we're so data oriented these days. A couple other things that I wanted to chat about really quickly. One administrative topic. Our resident philosophy professor, Drew Van Land, he's centered at Allegheny campus. He is going to be offering in the fall a new course, probably an experimental course. I don't know exactly how he's billing it, but Philosophy 206, Philosophy of Science. So I'm pretty sure right now we have like a Philosophy 101, just kind of a general intro to philosophy. And then I think it's maybe Philosophy 105 is Logic. I think those are really the only two philosophy courses we offer. So he's trying to start fleshing out the philosophy offerings at CCAC. And honestly, I think this is a great course for anybody going into the sciences. It's kind of roughly speaking, taking a look at, what is science when we make one claim versus another claim, or when we make a claim supported by certain statements or evidence or whatever it may be versus other statements or evidence. Um, how do we distinguish between, is this a statement based on science or not? Is it a, pseudoscience, the popular term, or is it like a misinformation thing? Or so looking at a lot of these ideas that I think are pretty relevant today. I mean, I've mentioned last week that I think one of the challenges today is less about acquiring information and more about curating it. You have 50 different ideas that are presented to you, and you have to decide which, two or three to kind of give more weight to. So I think this would be a really valuable course for anybody going into the sciences, or really for anybody just interested in being a little more aware of what, kind of what's going on out there, right? There are a lot of things that are presented as science that maybe are a little bit dubious. So, I don't know much about the course at all. The fall schedule isn't published yet, so this is just kind of a primer, just saying, hey, this is going to be out there. I'll probably bring it up again when the fall schedule is published and when you might be thinking about registering. But just to put it on your radar, it's kind of an interesting course, hasn't been offered before, and I'm on a general education committee with Drew, and that's how I found out about it. So you're probably the first students, probably aside from his current philosophy students, to know about this course. So if you're interested, keep an eye out for that. If you want me to put you in touch with Professor Van Land, you can shoot me an email. I can get you in touch with him, or you can, wait until it's published. Obviously, days, times, all that stuff aren't, even modality, I don't think is set yet. The schedule's not set yet. So a lot of the details are still up in the air, but just kind of putting it on your radar. Oh, cool. Yeah, glad that you're excited about it. Yeah, I think Drew and I have had some really interesting conversations, and you know, we're of a similar mind on this like Gen Ed committee. So I feel like, you know, I, I've told him before that I think that philosophy really complements really anything in STEM very well. Um, so, and then the third thing that I wanted to kind of mention, this I also just happened to come across and thought that it applied to some stuff that we had talked about before. I was watching a lecture from a history professor. He's a professor at Emory, older guy. He's, like what you would call a baby boomer, like, probably born shortly after World War II. And kind of long story short, he's interested in history, so he wanted to interview his dad. He wanted to basically write his dad's like life story, and he talked with his dad about the war. That was one of the things that came up, and his dad was in the war, and he said that it really struck him at one point during this interview. Now, this is one person's perspective on this. He's also a British guy, so his dad was in the Royal Air Force, so um, the kind of boots on the ground, so to speak, were much closer to them than say to the U.S. But he said it really struck him that especially in his generation, there's a huge survivor bias that the baby boomer kids were the kids of mostly the survivors of the war. But his dad was talking about how, his dad's like, basically all of his friends from high school had died in the war, and he was like the only one of his like group of friends to have made it through the war, and he's the one that procreated, and so uh, the thing that struck him was, is there a survivor bias in our perception of the impact of war and how terrible war is, that, at least in some sense, the the children of folks tend to be the children of survivors more often than the children of the folks who didn't survive. Is there a bias in the sense that we say, oh, well, my loved one survived, so, war isn't as bad as if my loved one had died? Is that our perception? And is there also a perception in that folks who were in the war and survived a lot of times don't want to talk about it? So, so that information is kind of cloistered away in those folks' minds. So I thought it was really an interesting point in it. This statistical topic of survivor bias, he even specifically called it survivor bias, came up in, an area where you might think is so completely remote from statistics, a study of military history or history of England and, I don't know, the early 1900s to mid 1900s. So thought it was kind of interesting that came up from a history professor. Uh, but anyway, and I had never heard that example of survivor bias before. And I think it's, again, I don't know if anybody studied this carefully or not. Maybe it's not borne out in the data, but it seems plausible anyway. Okay, so moving on then. Just a reminder, we were working on measures of center, and we had talked about the mean, the median, and the mid-range. We had our data sets, our tax return data that were considered populations, and our salary data that were considered, or that are considered a sample. And just a super quick reminder, because it has been 5 days since we've seen this material, some notation. X1 is less than or equal to x2, less than or equal to out through xn is our data set. Of size n. And our mean, our average, is either x bar or mu. Mu calculated the same way as x bar. X bar, our sample statistic, our sample mean, and mu, our population parameter. Geez, my writing is really not that great this morning. Not crossing it out, underlining it. Mu calculated the same way, but we give it a different name because later on it will be important. Our median is the middle number. Middle in the sense that once we order our data set from smallest to largest data value, we kind of cross off the lowest and the highest, cross off the next lowest, the next highest, and so on. And we work our way down till if we have an odd n, we get to a single data point, and that data point's value is the median. Or maybe we have an even sample size and we get to 2 middle data points, then we average those two. But it's the middle number in that sense as to what the median is. We just start chopping off the extremes, working our way in. And the mid-range is the average of the extremes. The mid-range only looks at the extremes. X min plus X max over 2. And something we noticed looking at our three different data sets, we kind of see that Ashley is pretty consistent, right? Her mean, median, and mid-range were all exactly 8, but also like a bad day for Ashley or a good day for Ashley isn't too far away from her typical day. Brandon kind of has, a bad day for him is pretty bad, but a good day is pretty good. So Brandon's performance is more variable, but his mean was the same as Ashley's. His median and mid-range, though, were a little bit different. In the salary data, we notice there's kind of a big cluster of folks. 5 of these 7 data points are all kind of clustered around the $25,000 to $30,000 range. There's one data point that's a bit higher, 55,000, to say roughly double the size of that kind of typical range. And then another data point at 100, double still the 55. So we look at this and we think, okay, this 100 seems to me like an outlier. It seems like it doesn't really fit in with this cluster of data and maybe even the 55. And we saw that indeed the salary data had a certain median. Its mean was a bit bigger than the median, and its mid-range was quite a bit bigger than the mean. So this might bring up a question then. What's the relationship between the measures of center, the 3 measures of center we just discussed, and skewedness? In other words, if we have a data set that is, say, skewed right, can we predict something about the measures of center? So for example, if we're right skewed, remember what this means is that we have outliers to the right. It means that maybe we have a cluster of data over here, and then we have a couple of data points that maybe don't fit in with most of our data, and they tend to be on the right side of that cluster. That was what we called right skewed in chapter 2. We're trying to make this a little more objective, right? So saying just look at the picture and decide if you think it's right skewed is pretty subjective. We make it a little more objective by relating it to these measures of center, mean, median, and mid-range. Of course, the measures of center are very objective, what the value is. There's just a computation. Can we draw a parallel between these two? And one thing that I notice is that among these 3 measures of center, the median is kind of like an anchor. So when I'm computing the median, the first thing I do is I chop off one largest and one smallest value, and the next largest, next smallest, next largest, next smallest. So when I'm computing the median, the first thing I do is I remove from consideration this right outlier and one of these left bits over here, and I remove this next right outlier and another one of these leftmost bits. Essentially, my outliers all just get chopped off and removed from consideration completely when computing the median. The median essentially ignores outliers. Almost by definition. I mean, the only way that the median will be affected by outliers is if, say, more than 50% of our data were outliers. But if more than 50% of your data are outliers, it's really hard to say that they're still considered outliers than if half of them satisfy that criteria. On the other extreme, the mid-range only looks at the extremes. So the mid-range places all of the weight on this and this. The mid-range is going to be the most heavily affected. And the mean is going to be kind of in the middle. It still has an effect coming in from the outlier, but that effect looks like, say, x max over n, right? If I have a sample size of 100, if n is 100, the effect of that, say, rightmost outlier, that biggest positive value, is diluted by a factor of 100, whereas in the mid-range, it's diluted by a factor of only 2, and in the median, it's completely ignored. So in the mean, we have maybe a moderate effect from the outliers. So my mid-range is going to kind of chase the skewedness. If I'm skewed right, if my outliers are to the right, my mid-range is going to be way out here to the right. My median is not going to care at all as effectively. Whether this data point was here or tucked right over here, the median is going to be exactly the same. And my mean has a moderate amount of effect seen. Right? It's still influenced by that outlier because it still pops up in the calculation, but it's not as heavily influenced because that effect is diluted by all of the other data points, where the mid-range is only looking at 2 data points. So we can say if the data set is right skewed, then we expect the mid-range to be quite a bit larger. I'll use greater than to indicate quite a bit greater than the mean. And I expect the mean to be quite a bit greater than the median. I expect this alignment in my measures of center if I have a scenario where I'm looking at right skewed data. And vice versa. If left skewed, if I have outliers to the left, I'd expect just the opposite. Then I'd expect my mid-range to be way off to the left. I'd expect my mid-range to be a lot smaller than my mean, and I'd expect my mean to be a lot smaller than my median. So my median is kind of the anchor, and the mid-range is getting pulled around the most. The mean is getting pulled back and forth a little bit, and the median is just kind of staying still and ignoring the outliers. So we have this direction of logic, an if-then statement. If we have a certain skewedness, then we can make a statement about the measures of center. Can we reverse that logic? The answer is, precisely speaking, no. If we were in algebra or calculus, we'd say, okay, this is a one-directional logical statement. This is A implies B. From that, I cannot conclude that B implies A. I can't reverse the direction of the logic because it doesn't work in all cases, right? If we say, say we had a perfect world and we say, all dogs have 4 legs, we say if it's a dog, then it has 4 legs, and that would be a true statement in our utopia. But we can't really say if it has 4 legs, then it has to be a dog. It could be a cow or a horse or a cat or something. So we can't just reverse logical implication. We can't reverse if-then statements and say if the measures of the center line up this way, then it must be right skewed. But in statistics, we're a little fuzzier with our logic, right? We talk more in terms of evidence in favor of a certain conclusion versus evidence against a certain conclusion. We're a little less rigid in our logic, and we talk more in terms of evidence in favor or against. That has pros and cons. The one pro is that it applies much better to the real world, where precise logic essentially never it never completely works out, right? Precise logic is always a model that we overlay on the real world. The world doesn't obey the logic that we just say that it should obey. Um, so that frees us up to make evidentiary statements about the world. But on the other hand, when we start making these types of statements, we really can't make any guarantees. It's just a little less comforting for somebody to say, well, I'm pretty sure that this isn't going to happen versus saying, I'm absolutely certain it's not going to happen. So what conclusion might we make here? If we're trying to develop a test for skewedness, if I ask you, does this data set exhibit skewedness? Your chapter 2 answer would be, well, plot a histogram and see if it looks skewed to you. That's pretty subjective. At least a little bit more objective would be something like, if the mid-range is much bigger than the mean, which is much bigger than the median, then we conclude that there is evidence in favor of right skewedness. We certainly wouldn't say this is evidence in favor of left skewedness. But if I look at these, there's still a little bit of subjectivity here, right? What does it mean to say that the mid-range has to be a lot bigger than the mean? Is that like 5% bigger or 10% bigger or double the size? What about the mean versus the median? How much bigger? And similarly, if the mid-range is a lot smaller than the mean, which is a lot smaller than the median, then we have evidence in favor of, so here the mid-range is way off to the left. The outliers are pulling the mid-range to the left. That's evidence in favor of left skewedness. And if our measures of center, if the order is jumbled up, or if they follow this order, mid-range, then mean, then median, but maybe those three numbers are pretty close together, then maybe we would say lack of evidence of skewedness. So if neither of these, then there's a lack of evidence of skewedness. Right. So the skewedness question isn't binary in the sense that it has to be right or left skewed. It's actually, I would say the typical or maybe the default case would be that we don't see evidence of skewedness, and then occasionally we see some right skewedness, or occasionally we see some left skewedness. Any questions on this? So we have a slightly more objective test for skewedness now. We can look at the way that these three measures of center line up, and provided that, we decide how we want to interpret, substantially greater than, we can come up with an assessment of skewedness on the basis of these numerical descriptors. Okay, let's talk about another measure of center, the mode. So what is the mode? Remember, in the measures of center discussion, we're trying to say something like, what does the typical data point in my data set look like? What does the typical data value look like? The mode is the most frequently occurring data value. This seems like a pretty reasonable thing to say. It does have some challenges, though. So it's the data value that has the highest frequency. Let me look at my Ashley and Brandon data. Well, Ashley's data is 5, 7, 8, 9, 11. Which of those data values has the highest frequency? They all have frequency 1. They all appear once. If I have continuous data or even discrete data that has just a lot of different possibilities, a lot of different like bins that the data point could fall into, I don't know if the mode is really even going to exist, right? So these tax return data, these would have no mode. Uh, I mean, it would be kind of silly to say that all of the numbers in the data set are the mode, so we say it has no mode. The salary data, it looks like 28 would be the mode because it occurs 3 times. Everything else only occurs once. So there's a sense in which that could be a typical data point. But what if the only reason this occurred 3 times was, these 3 people happen to have the same job title or something, so they get paid the same amount? Is that really what we mean by a typical data point? It might be in some contexts, and it might not be in other contexts. Kind of even worse than that, you could imagine a situation where we're, say, rolling a 6-sided die, and we get a histogram that ideally would be perfectly straight across, and we would get no mode, right? We'd ideally, in a perfect scenario, get exactly the same numbers of ones through sixes. But in reality, we're always going to get a slight deviation from that perfect uniform distribution. So here, 5, just by chance on this, say, 120 rolls, occurs just ever so slightly more often than the others. Well, 5 is the mode here then, right? But in something like this, the mode is just completely random. You roll another 120 rolls of this same perfectly fair die, and maybe 1 will be the mode next time. The mode doesn't say anything about a measure of center here in a uniform distribution where I just have a tiny bit of sampling error. My mode could be anything. Now, if I have a situation where my data have a naturally clear peak, maybe sampling error cuts this peak down a little bit, but it's still going to be the mode. Or maybe even this peak gets cut down and this next bar over here gets a little more frequency in a certain sample. Maybe my mode shifts from here over a little bit. So if I have like a normal distribution or a bell curve situation, maybe my mode makes a little more sense. Maybe it's a little more like a measure of center. If I have a curve that I'm using to define my frequency distribution, in the mathematical sense, I can find the maximum value of that curve, uh, and that gives me the mode. So that's a pretty well-defined problem when I have a nice continuous function like this that I've used, that I've overlaid on data or something to model it. But I think the kind of clearest benefit from the mode comes in something like this. If I have categorical data, say from shirt color observations, say red, green, yellow, and blue, I just look at people walking past and check off the color of their shirt, and I have uh, for this data set 5 reds, 1 green, 2 yellows, and 2 blues. If I have to send uh, send a design off to a factory and have it produced, and I can only pick 1 color, which color should I pick that I think will probably sell the best? Well, red has the highest frequency of 5, so the mode, be careful, the mode is not 5, that's the frequency. The mode is the most frequently occurring data value. The mode is red. One really nice thing about the mode is that I require absolutely no structure to my data, right? If I want to compute a mean, I have to be able to add my data together. I certainly can't average a bunch of RGs, Ys, and Bs. I can't take the mid-range either. That's an average. I can't even do a median. I mean, if I could order these, I could do a median, because I could say which one is lowest and highest and then start chopping them off and making my way toward the middle. And I suppose so long as I didn't have to average the two in the middle or something, I might be able to talk about a median if I could order them. But I can't even order these. These these data don't have enough structure to do any of these previous measures of center calculations, but I can compute a mode just fine because the mode looks at the frequency. The only thing I have to be able to do is set up a bin and count the number that went into that bin. And the mode is using the numbers it's using are the frequency numbers, which are counting numbers that are separate from the data, obviously associated with the data, but we're not trying to like average or order RGYB. We're ordering the frequencies 5, 1, 2, and 2, and we can order that. Those counting numbers for the frequencies do have an ordering to them, and I can see which one is the highest. The frequency of 5 is the highest, so the mode is the data value associated with that frequency, namely red in this case. So the mode works when in some situations when other measures of center don't work. But we want to keep these caveats in mind that if we have a roughly uniform distribution, the mode is essentially random. And we really can't in any reasonable sense call it a measure of center. There are also situations where we have distributions with kind of two peaks, and we'd often call those bimodal. We talked about this in chapter 2, but where do I draw the line, right? If I have, say, 3 peaks and a data set of size 100, I might say that that's trimodal. If I have 5 peaks and a data set of size 5, that just means that every data value occurred once, then I say there's no mode. So like it's kind of fuzzy where I draw that line between, when does the mode make sense to use and when does it return something meaningful and when does it just kind of return something random or something arbitrary. I don't think it's super clear. But I think the cases where the mode is good to use is something like this, where at least it appears that this is not a roughly uniform distribution of red, green, yellow, and blue shirts. Seems like there's definitely a preponderance of red over the other ones, and where the other measures aren't really able to be used. Any questions on that one? Okay, then next up, the weighted mean. This is a generalization of the average. Generalization of the mean. So remember, for instance, x bar, or mu, is x1 plus x2, and so on, plus xn over n. Or really, this is kind of like 1x1 plus 1x2 plus 1xn over 1 plus 1 plus 1 n times. So in an average, in a mean, I'm giving all of my data points equal weight, right? If I say, what's the average height of people in Pittsburgh? If I take my sample of size 100 and I measure each of those folks, if I add them all together, divide by 100, that gives each person, each measurement, equal weight. What if I want unequal weight for some reason? One example might be with scores in a class, right? So maybe exams and homeworks and quizzes and so on are weighted differently. Maybe some of them are weighted more heavily and some less heavily. Or another example might be, if you look at, say, global temperature data, try to draw something resembling a circle. If you look at global temperature data, maybe you have like the US here, and maybe we have lots and lots of temperature stations all over the place, right? So we get lots of data points from the US, But then you look in the middle of the Atlantic Ocean, and I do realize there are other countries in the world other than the US, but I'm just not going to try to draw much more. But then you look in the middle of the Atlantic Ocean, there's going to be much lower density of, say, weather monitoring stations or temperature monitoring stations in the middle of the ocean, right? It's just a lot more costly to upkeep or install or monitor. Well, I probably should overweight these and underweight these then, right? In essence, each of these little temperature stations is only kind of accounting for a very small number of square miles of area that it's kind of representing, where each one of these has to account for a much larger amount of square miles. So how should I weight these? Well, I probably want to, and probably should do things a lot more precisely than my hand wavy way of doing it here, but you'd want to overweight these ones in the middle of the ocean and underweight the data points that are, all over the US. We wouldn't want to just smash all of these together and take their average, because then we'd be, you know, naturally overweighting the influence of the temperature in the US and naturally underweighting the influence of the temperature in the ocean, just because of the amount of data that's represented in one versus the other area. Okay, so weighted average. How do we compute a weighted average or a weighted mean? Well, first we need to have data points, x1 through xn, and we need to have associated to each data point a weight. This needs to be given as part of the problem. So we see here we have data points, homework, our score was 90%, quiz is 50%. These are our data, x1, x2, x3, and x4, and they're associated with weights. The weight for homework was 30%. That's W1, W2 for quizzes, W3 for midterm, and W4 for final. These are not the weights for our course. We don't have quizzes, so don't be worried if you're like, wait, I didn't take a quiz yet. You didn't miss anything. I'm just using this as an example. So we need to have data with corresponding weights. It's important that, weight W1 goes with X1. It's not just a random list of weights and a random list of data. And then we can compute our weighted mean as follows. We take W1 times X1 plus W2 X2, and so on out to Wn Xn, and we divide that by the sum of the weights. So we actually see that the mean, this is just a weighted mean, where the xi's, or sorry, where the wi's are all exactly equal to 1. The average, the mean, is just a weighted mean where everything is weighted equally with weight 1. And we could really even get away with just saying the weights are all the same number, I guess supposing that a is not 0. Because if I had a factor of a everywhere on top and everywhere on the bottom, it just divides out. So anytime that I have a weighted mean, but I'm weighting all the data equally, whatever the weights are, if they're all weighted equally, then that just becomes the special case of the mean, x bar, the arithmetic mean, the average, however you want to say it. Note that if I make W2 through Wn minus 1 equal to 0, and W1 and Wn equal to 1, that recovers the mid-range. So the mid-range is also a special case of the mean. I suppose you could, really press the issue and say that maybe the median is also a special case of the weighted mean. Although we'd have to have a couple different cases for even and odd and so on, but you can probably say that as well. I have another special case that if the weights add up to 1, well, then something really nice happens. The denominator is just 1. I have a numerator over 1. Well, that denominator just goes away. So a special case, if all the weights add to 1, the denominator goes away, and that's just my weighted mean. Just the multiply the two things together, the weights times the data values, and then add them up. So you'll often see in things like syllabi that we'll choose weights that add to 1 so that we don't have to have this crazy denominator floating around. Some folks prefer like a point system where, there's 3 exams that are worth 100 points each and a final exam worth 200 points and, 10 homework assignments worth 20 points each. They prefer a point system like that. It makes it a little easier for the instructor to kind of like, nudge things around back and forth and get it the way that they want. And it also, from the student's perspective, they can look at it as, okay, I've done this homework set, I've accumulated this number of points, and they can see like how many points they have in the course so far and how many they need for whatever grade. But then the calculation of the grades gets a little bit wonky, right? It's, you say you have to have 472 points for an A or something like that, and it becomes a little bit unclear how likely it is for you to get that many points given how many points you've already earned and how far we are through the semester. So there are definitely pros and cons to both approaches. I like using the percents approach. But we note here that the weights do add up to 100%. We will write everything out explicitly here, but we could get away with using this special case formula. So what is our final course grade? Or in other words, what's the weighted mean, the average of our actual scores on these assessments, but weighted by these weights. So with the final exam being weighted, say, more heavily than the quizzes. Well, it's going to be W1X1 or 0.3 times 90 plus W2X2, 0.1 times 50, W3X3, 0.2 times 75, and W4X4, 0.4 times 80. In the denominator, I have the sum of my weights, point 0.3 plus 0.1 plus 0.2 plus 0.4. Okay, let me bring up the calculator, adjust my screens here a little bit. Right. And let's plug this in the calculator. So in the numerator, we have 0.3 times 90 plus 0.1 times 50 plus 0.2 times 75, and then plus 0.4 times 80. And this gives us a 79%. My denominator is 1, so I just didn't enter that in the calculator. And these are our scores as percent, of course. So they carry the unit of percent over here. So our final course grade would be 79%. If we wanted a B, we would have to increase one of these scores by a little bit. So what if, let me copy this down here. What if, for instance, I need to give you a midterm grade? So we have a midterm exam in the course. You get a grade on the midterm exam. It's through my stat lab and all of that. I think we have two midterm exams, exam one, exam two. Um, we have a final exam in the course, but we also have something that's just college-wide called a midterm grade. Note that there's a difference between your midterm exam grade and the midterm course grade. If you go onto myccac.edu onto the portal, you can find your midterm course grade halfway or so through the semester. And that's an estimate that your faculty member gives you in each of your classes as to how you're currently doing. It is not the same thing as your midterm exam grade. So maybe we get to midterm course grade time, and maybe you've completed, say, half of your homeworks and have an average of 90% and completed some quizzes and have an average of 50 and completed maybe in a different course, say a single midterm exam with a 75, with a grade of 75%. But you haven't completed your final exam yet. Obviously, it's the middle of the course, and we're trying to give a midterm course grade. So how should we compute your midterm exam or your midterm course grade? One kind of note on this is a very ill-posed problem. I actually don't like giving midterm course grades because there are so many different ways to that you could argue is the best way to compute it. But a way to compute it is probably the most standard way, probably the way that I think most of your faculty would use, is they would take a weighted average of the data that they have. So your midterm course grade, they would weight these three data points with these three weights. We don't have any information for the final exam, so we ignore that data point and its associated weight. So I'd have 90 times 0.3 plus 50 times 0.1 plus 75 times 0.2, and then I divide by 0.3 plus 0.1 plus 0.2. Be really careful, this is no longer equal to 1, so we can't just get rid of the denominator anymore. We need to divide by 0.6. So coming over to our calculator, our numerator is 90 times 0.3 plus 50 times 0.1 plus 75 times 0.2. That looks right. That's our numerator, and we divide that by 0.6, or about a 78.3%. So when you look at your midterm course grades, practically speaking, if you expected an A and got a B, or you expected a B and got an A, I wouldn't give a whole lot of weight to that difference. But if you expected an A and got a D, or if you thought you were failing the class but got a C, if you're more than if you're say two or more letter grades away from where you would expect, maybe then look into it, check your calculations, reach out to your professor and ask them, either I'm doing worse than I thought I was. Did I miss something? Is there something I can do to make up that ground in the second half of the course? Or if you're doing better than you thought you were, double check, make sure all the calculations are right, and good job, you're doing better than you thought you were. So, but that's how I think most folks would compute their midterm course grade. Now, it's a fair question. You could keep digging here and you could say, well, but you've probably only completed like half of your homework for the course, halfway through the course, and half of the quizzes, but you've completed like all of the midterm exam. Would it make more sense to make this 15%, this 5%, and this 20%? Because for the homework and quizzes, you've only completed half of those assessments. You still have half of them to go. But for the midterm exam, you completed that entire assessment. That 20% is already in the bag. Would that be a more sensible way to do it? Would it be a more sensible way to do it to say estimate your final exam score using your midterm exam score. Because that's basically what leaving these weights at 30 and 10 is doing. It's basically saying I'm estimating your second half homework scores using your first half homework scores. And I'm estimating your second half quizzes using your first half quizzes. If I leave these at 30 and 10, keep this at 20, then that's kind of in parity. Should I keep this at 40 and make this 75? Estimating your final exam performance using your midterm exam performance. Would that be a sensible thing to do, right? So kind of, even though this basic weighted mean approach, this one here that we did the calculation here, this seems like the most obvious way to do it. It's probably the most obvious way, but it has some difficulties, right? I mean, really, these are kind of on a different scale than this one. So it has some shortcomings, but to resolve those shortcomings means essentially picking an arbitrary way to resolve it. That's not so great either. So this is why I don't like midterm course grades. And this is why I say, take midterm course grades with a grain of salt. There are a lot of choices that your faculty member can make, and they're trying to communicate to you, like, if you're doing 2 or more letter grades off of what you expected, that should be a bit of a wake-up call. But if, I wouldn't quibble over a 1 letter grade difference. It's really not that granular. Now, of course, once you get to final course grades, then everything is known and everything is calculated exactly as in the syllabus. Then everything is completely objective. There's no, decision on how should I do this or that. It's all right here. But for midterm grades, we're trying to say something like, if you keep working in the second half of the course at about the same level of effort as you worked in the first half of the course, what grade do I think that you'll end up with? And as you can suspect, that's quite a subjective question, and quite a difficult question to answer very clearly. I don't think most faculty outside of math or maybe engineering or something have thought this much about their midterm course grades, so they probably just calculate them, this way. But okay, yeah, let's discuss this just a little bit. So minor aside here, we have enough time for this, so take maybe 5 minutes here. This is a really interesting topic that we could go into more depth in. I kind of gave a little bit of insight when I was talking about the mean being a special case of the weighted mean, and also the mid-range being a special case of the weighted mean. You might go up here and you might say, man, we have so many different kinds of measures of center. It seems like we're just making stuff up here, right? It's like, oh, well, these 3 didn't give me the number I wanted, so maybe I'll come up with another one and see if it does, or maybe I'll come up with another computation and see if it, gives me the thing that I want to get out of it. Gives me a number that makes my performance look good or something. But actually, all of these measures of center, and even some others like RMS, root mean square, used often in physics and electronics and so on, the quadratic mean, these are all linked together from a more foundational concept. The same way that, the mean, the mid-range, perhaps the median are special cases of the weighted mean. These concepts are all special cases of a bigger idea. And the bigger idea looks like this. If I want to find m to minimize, let's just first look at something like this. x1 minus m squared plus x2 minus m squared, and so on. These squared deviations from the measure of center. If I want to minimize these square deviations, the m that does this is the one that's computed exactly as x bar. You can either use some basic Calc 1 calculus for this, or you could actually recognize that this is just a quadratic opening downwards in m. And you actually could just use um, algebra 2 and understanding quadratics and so on to come up with this answer. Um, Figure out where the vertex is, and there's your minimizer. Or sorry, quadratic opening up. Um, Quadratic opening up, we get a minimum. So you could find this using algebra or calculus. What if I wanted to find, let me call it maybe capital M, to minimize absolute value of x1, make that a big x1 minus m plus absolute value of big X2 minus m, and so on. If I want to minimize these absolute differences between each of my data points and the measure of center, it turns out that m equals the median. What's kind of common with these two ideas? Well, what's common is that if I imagine I have some data points over here, if I set a hypothetical measure of center, and I look at the distance that that measure of center is from each of the data points, if I'm calling it a measure of center, it should be kind of in the middle, right? Like I wouldn't want it to be way over here for data that are, you know, that are in this area, or I wouldn't want it to be way over here. It should be kind of in the middle of the data. If it's in the middle of the data like this, well, I have a distance from this measure of center to each data point. Some of them are going to be positive and some are going to be negative. So I want to take the negative ones and make them positive, and then I want to somehow accumulate them. And I would like to wiggle my potential measure of center around until I find one where I have the smallest kind of absolute distance to my data points. That's when I've chosen the point on the line, the point on the real line that is in some sense, pretty close to all of the data points. That seems like what a measure of center is trying to do. How do I take the negative distance and make it positive? The distance is what looks like the xi minus m. I could make it positive by taking an absolute value. I could make it positive by squaring it. So if I sum up, say sum L of xi minus m, where L takes negative numbers and makes them positive, if L is the absolute value function, so L is sometimes called a loss function. It's a penalty incurred for the measure of center not being directly at that data point. The further the measure of center is away from a given data point, the higher the penalty. That seems pretty reasonable. We don't want to measure the center that are really far from lots of data points. If I choose as my loss function the absolute value function, well, that yields the median as the measure of center that I'm most interested in. If I choose the loss function to be the quadratic, just take the thing and square it, that yields the mean. There are some others that are a little bit more complicated to explain how they work. So for instance, the mode, it's kind of a little bit like taking the infinity power a little bit. Something like the mid-range, or the mode is kind of like taking the zero power, and the mid-range is kind of like taking the infinity power a little bit instead of the, say, basically first power or second power. And there are others like the harmonic mean and the geometric mean that have a loss function that looks a little bit more wonky, but is closely related. So we get all of these by doing this. Find little m to minimize something that looks like adding up the distances that m is from each data point. I want m to be kind of close to each of the data points, kind of, according to some metric. That metric might be quadratic, it might be an absolute value metric, it might be a maximum or minimum metric, like an infinity power kind of thing, or it might be some other metric. But all of these measures of center come from this structure, and just choosing different ways to measure this distance. It's a little bit like, not exactly, but a little bit like, do we measure it in feet or meters or centimeters or something like that? So, so there really is one underlying structure giving rise to all of these superficially seemingly very different measures of center. And this is really what math is all about, is generalization through abstraction. We realize that we build a couple measures of center because we like how they work. We dig a little deeper, we find out their relationship, and that lets us understand the relationship between many more measures of center, all being related by this idea of minimizing some loss function. Okay. So they are all connected. They're not just kind of randomly plucked here and there with no rhyme or reason, even though at the surface level they seem like that. Okay, I think for time considerations, we are going to, I'm going to post a supplemental video on geometric and harmonic mean. So take a look at the YouTube channel in the next day or so. That'll be up there, and shouldn't be that long. Geometric mean is important for some things like finance, particularly things where you have that, like, remember where the semi-log chart and the log chart were beneficial. That's where things like geometric mean are tend to come into play. And harmonic mean also has kind of a specific application, so we'll talk about those in a supplemental video. All right, but any questions on measures of center before we get down to measures of variation?
I have a question, but it's
Yeah.
not based on the topic we're on about right now.
Okay, is it about statistics or is it?
It's about the class, me being confused since I missed 2 weeks of it.
Okay, maybe send me an email or pop in office hours for that one.
Sounds good. Thank you.
Okay, yeah, sure. Okay, the other thing I want to do to wrap up 3.1, let me just switch my screens around here. I want to take a look at computing some of these measures in Excel. So I'm going to pop an Excel file into the chat. Oh, I need to close it first. Okay, so I put an Excel file in the chat. I had it open in the background and needed to close it before it would let me pop it in there. So you can follow along on Excel, and we'll look at how to compute some of these measures of centers for these same data sets using Excel. All right, so you see in here I have the data sets entered already. The Ashley and Brandon data, we're saying those are populations. They're already listed. The salary data are also already listed here. So the salary I have ordered from largest to smallest, the Ashley and Brandon from smallest to largest. Doesn't matter a whole lot when we're entering into Excel how things are ordered. having things ordered helps us a lot when we're looking at it, just typing things in or working through even some of the 3.2 material. It's helpful for us, but for something like Excel, it doesn't really care what order it's put in. And I can look down here, I can compute, say, the mean, the median, and mid-range for these different data sets. Now, the first thing I might want to do is go ahead and rename each of these data sets just to make them a little easier to refer to. So maybe I'll select the Ashley data and come up here just above the A column marker and name this something like A data for Ashley data. Hit enter. And do the same for Brandon. I've already named it Brandon, but can I rename it B data? I think it might not be happy if I do that. Okay, yeah, let me rename it B data. Yeah, if you want to reuse a name, then it's a bit annoying to. So like if I had accidentally like selected this and named it B data, and I was like, no, I actually want to use I want to call this B data, then it's kind of annoying to try to reuse the same name. Um, but okay, we renamed these cells just fine, B data. And then salary, I'll rename it S data. I think I did it not let me do that. Hmm. All right, well, we'll just leave these cells named salary. It doesn't want to call them S data for me for some reason. Um, you can go up into the data tab. Where is that? Is it? I'd have to poke around in here to remind myself of where that there's a place you can get to all of your cell names and you can find the one that you don't want to just click on it and delete it and then start from scratch. But anytime that I do that, I have to go to Google and do like, delete cell name or something like that. Um, and then, the AI prompt comes up and says, oh yeah, just go to this menu and that sub menu. And so I always forget how to do it because I do it, once every 6 months or a year or so. But I have my Ashley data that's named A data. And for me, remember, I want Excel to compute something, so I've got to start with equals, hit the equal sign. And Excel's built-in formula for mean is average. And if I hit tab, it puts the parentheses in for me. And so there's average of, and I'll use the A data label. I'll end the parentheses. And I see that the mean of the Ashley data is 8. I could compute her median as well, equals median of, and if I wanted to, I could just click and select the data if I wanted to do that. Or for the mid-range, there's not a mid-range built-in function, but there is a max built-in function. And there's also a min built-in function. So I can just use these two built-in functions max of Ashley data plus min of Ashley data. That is the numerator of my mid-range, x min plus x max. And I want to divide by 2. I might be tempted to just come over here and divide by 2, but that gives me a number that I don't recognize from last time. I think I should get 8. Excel respects order of operations. So what we're telling Excel to do is take the minimum 5 divided by 2, you get 2.5, add it to the maximum of 11. Well, that's not what we want. We want the entire numerator divided by 2, so I better put another set of parentheses around that numerator. So I have max of A data plus min of A data, all in parentheses, all divided by 2, and that looks better. I can drag across. I noticed that the reference is still A data for the Ashley data, but I can pretty easily just change that to B data. Remember, Brandon's had the same average. Or, and I guess this one I have to call salary, if I can spell it correctly. There we go. And that was my average for the salary data, $42,000. And I could do the same for the median and the mid-range. Just being careful to adjust those cell references. I can actually grab the edge of the blue box up here. Not displaying it super nicely for me, but maybe because it says A data, it's not wanting to let me do that, but usually you could grab the edge of the blue box and just kind of pull it over. But now we have the median of the Brandon data. And the mid-range of the Brandon data. So we see that Ashley's mean, median, or mid-range all exactly the same, indicating really no evidence of skewedness at all. And I think we'd agree with that looking at our data set. This is certainly a small enough data set we can just kind of inspect it and see that it doesn't look like there are any outliers. The Brandon data, median is at 7, mean a little bit higher, 1 unit higher on a scale of 7, 15% increase. Mid-range a little bit higher still, half a unit on a scale of 8. And what is that, 7 or 8% increase? So maybe the mean, median, and mid-range line up the right way to indicate a little bit of right skewedness. But in my mind, 14, 15% increase and then a 7 or something percent increase is not a large increase from the median to the mean or from the mean to the mid-range. So I wouldn't really call this evidence of right skewedness, but somebody could disagree, right? This is still a little bit subjective. What do we mean by substantially bigger than? And then our salary data, can compute the median as well as the mid-range. And here I see going from the median to the mean, 28 to 42, is a 50% increase. That's probably a pretty substantial increase by most people's metric, I think. And going from 42 to 62 and a half, that's about a 20-point jump on a scale of 42. Again, about another 50% increase. So the mean is about 50% larger than the median, and the mid-range about 50% larger than the mean. I think that we have some evidence of right skewedness here, and that I think most people would say is borne out in the data as well, that this, having 5 of our 7 data points clustered between 25 and 30, and then having a 55 and then a 100 that are kind of out there by themselves, maybe some evidence of right skewedness there. If we wanted to, look at a weighted mean, we could look at this example over here, where we have a person's performance on their 4 different assessments, along with the associated weights for those assessments. I don't remember if this was exactly the same data set I used over here. I don't think it is. Oh yeah, okay, it does turn out to be. Oh yeah, 79. Okay, that. So we could take the numerator, which is G2, the homework grade, times H2, the homework weight. So that's what we have here. This is all in parentheses because it's the numerator, plus G3 times H3, the quiz grade times the quiz weight, plus the midterm exam grade times the midterm exam weight plus the final exam grade times the final exam weight, all in parentheses. That makes up the entire numerator. That's all of this over here, the numerator, divided by the sum of the weights. That's the denominator. So I use the built-in Excel function sum to sum up my weights. So I didn't have to do, what is it, H2 plus H3 plus H4 plus H5. And that gave me that 0.79 or that 79%. I could also use instead to do this multiplication across and then adding down. Excel has this really nice built-in function. It's kind of a special use function, but it's called a sum product. So the function sum product will do this for us. And really what we're doing here is something more generally in mathematics called an inner product. And that's the reason Excel has this as a built-in function. It's an inner product really of these two, if we think of them as vectors. So we take the sum product of these two columns, the grades and the weights, divided by the sum of the weights. Don't forget that little bit. The denominator still has to be taken into account. Gives us that 0.79 as well. So we can let Excel do a lot of the heavy lifting for us. And the other nice thing about Excel is we can do scenario analysis. So if I was saying, what do I need to get on a final exam to get a course grade of, say, 80 or higher? Well, I can try, what about 0.81? Does that do it? Not quite. What about 0.83? Okay, it's just over at 0.83. I think at 0.82 would be too low. Yeah, so I need an 83% on the final to get a course grade of 80% or higher, right? So if we code this in Excel this way, we can do a scenario analysis, or maybe I say, okay, what if I get my homework grade up from a 90% to a 93? Can I get away with a 75 on the final exam? Not quite, right? So I could do some different scenarios and say, what do I think I could reasonably get on the final exam? What do I still have out there for homework? How much could I boost my homework grade? And play with the numbers a little bit that way. This is related to the geometric mean, so I think we will skip over that for now. Any questions on this? I think the main thing in the Excel side of things is to be able to do mean, median, or just probably mean and median for a data set. That I think is the main concept from 3.1. Okay, let me switch my share back to just OneNote. Okay, so jumping into 3.2 now, the next section in chapter 3. Chapter 3 has a lot of material in it. It's a little deceptive because it like only has these main 3 sections in it, but each one of them has quite a bit of material. So 3.2, measures of variation. 3.1, the kind of motivating question was, what does the typical data point look like, or what does the typical individual in the population look like? Measures of variation is asking something like, how variable is the data set? Or maybe another way to put it is, how far can a person or data point, maybe something like reasonably, deviate from the center or deviate from typical, right? basically how strange are things likely to get. And so again, we have our uh, same data sets that we're working with in 3.2 as well, the tax return data for Ashley and Brandon and the salary data. Well, I didn't put these in order, but I didn't put the salary data in order. I thought I did. I have it in order up here. Let me swap that out. That does just make life a lot easier when the data set is already ordered. There we go. Okay, so everything is in order now. And we have a couple of measures of variation. The first one we have, super nice. It's nice and easy to compute, the range. The range doesn't get a special notation. It's usually just written range. And what is it? It's the difference of the extremes. It is x max minus x min. Note the close relation to the mid-range, both in the way that it sounds, mid-range versus range, but mid-range is a measure of center and range is a measure of variation. And also in the calculation in the sense that it only looks at the extremes. It only considers x max and x min in the calculation, but the mid-range averages the two. The range subtracts the two. What is the range doing? Well, the range is saying, okay, let's just look at salary data. I have 25, 28, 28, 28, 30, 55, and 100. The range is looking at the difference between the max and the min. It's looking at the swath of the real line covered by the data set. So this distance is the range. It's what part of the real line is covered by the data set. So in this case, the range for the salary data is going to be 100 minus 25 or 75. And that's in the units of the original data, thousands of dollars. The range of the salary data, $75,000. There's a 75,000 or 75 unit swath of the real line covered from 25 up to 100. Or I could ask you a similar question for Ashley or for Brandon. I see Ashley's maximum number of returns per day is 11, minimum is 5. The difference is 6, and that's in units of returns per day. Range gives me units of my original data, so 6 returns per day. And for Brandon, we see 14 minus 3. 11 returns per day. And that's something that we noticed in the last section about the Ashley Brandon data, that even though the two of them perform kind of on average about the same, or like the total number of returns they get done over, say, the span of a whole week is about the same, or in this case, exactly the same for these data sets for the two of them. And when Brandon has a good day, he has a really good day. But when he has a bad day, it's a really bad day, and Ashley is much more consistent. So when Ashley comes in on a given day, you're not likely to see anything strange from her either to the right or to the left. She's very consistent, where Brandon is like, has he had his coffee today, or has he broken up with his girlfriend this morning or something? Like, he's going to be all over the place. If he has a good day, it's going to be a really good day, or a bad day, it's going to be a really bad day, or it. So you can see much stranger things from Brandon than from Ashley. Brandon has a larger measure of variation in this case, a larger range. Brandon's range is almost twice that of Ashley's. It does make sense to compare the Brandon and Ashley ranges directly. We are comparing units with or data with the same units. both of them returns per day. They have kind of the same context. They're both tax returns, completed by coworkers. But we don't want to say like, oh, the range is much more variable than the Ashley data or something. It's different units. It's a completely different context, measuring completely different things. So comparing the two directly wouldn't make a whole lot of sense. But comparing, Ashley and Brandon and saying Brandon's performance seems to be about twice as variable as Ashley's on the basis of the range, that might be a reasonable thing to say. So the range has some positives. It's really easy to compute. It gets us a measure of variation. That's super nice. Um, it has at least one big downside though. And that's that, well, it only looks at two data points out of the whole data set. I guess with, a data set of size 5, maybe that's doesn't seem so absurd, but imagine you have a data set of size 10,000 and you're only looking at two data points to say some important characteristic about this data set. That seems a little bit silly. And the mid-range has the same complaint, right? It only looks at two data points out of the entire data set. So that's the big downside. That's the really big downside with the range is it's only considering two data points out of the whole data set. Right. So if Brandon came in and one day had an extremely great performance and the rest of the days was exactly the same, I mean, then his range would be really big, even though, I mean, maybe you can get that kind of performance every once in a while, but that's not going to be typical. So, so what we would like, maybe an ideal would be to develop a metric that has this kind of feel, the kind of the further spread out things are, the higher the value of it is, the higher that measure variation is, but that also like touches every data point. I wanted to consider every single data point, not just two data points out of the entire data set. And that's where the variance comes in. Now, in the 10 minutes or so we have left, I don't think we have time to really um, build up the variance kind of from first principles and then do an example. Um, so I think we will end class a few minutes early today. And then next time we'll start right into variance. Um, so we'll start right into like building this up from first principles, going through some calculations. The variance and standard deviation are going to be probably some of the more calculation heavy aspects of the course, just a lot of things to do. And we'll be using kind of a tabular format to help us with those calculations. So, get ready with your calculators and with your pencil and paper next time. We'll be doing some examples of variance and standard deviation, both on pen and paper and on Excel. So we'll continue working through this Excel spreadsheet with some of these measures of variation next time. Any questions before we break for today?
Yes, I